Hello everyone, I am Miss Amruta Jadhav ma'am, your physics teacher. I am welcoming you all to the part 9 of wave optics, in which we are going to deal with numericals. As you all know, all part 8 was about theory, which deals with all the theoretical part which is there in wave optics, and now in this lecture and this part we are going to deal with numericals. So let's move towards the numerical part. So here is the first one. The first numerical which we are going to deal with is unpolarized light of intensity I0 is made to pass through three polarizers P1, P2 and P3 successively. The polarization of P2 makes an angle theta 1. You have to remember these things, that's why I am underlining. With that of P1, while that of P3 makes an angle theta 2 with that of P2. Okay, first you have to remember all the concept which is related to polarization. What is polarization? When the unpolarized light means when the light is passes through polarizer, it will convert into a single beam of light or single term of light. That is nothing but polarization. Now in this case they have used three polarizers P1, P2 and P3, and they are making some angle with each other. Alright, so we have to consider all of that conditions, and we are going to find out the intensity of light coming out of P3. Okay, so unpolarized light of intensity I0 is there, which is passing through all the three polarizer, which is making some angle with each other. And what will be the intensity of light which is coming out of P3 by polarizing by all of this angle? So firstly what we are going to say is polarizer P1 will polarize the light, first one, after passing through polarizer. So here which I have written, polarizer P1, the first polarizer P1 will polarize incident light which is passing or incident on it, and then after passing through this polarizer, as we discuss all the theory about it, the intensity will be half of the original. So I1 will be I0 divided by 2. Let us assume now the amplitude of electric field will be what? For the first one it will be E10. For the second one, that is polarizer 2, it will be E20. So what will be that? According to formula it is this: E20 is equal to E10 cos theta 1. See, this is not we are going to include in this, but this is the theoretical part which is written over here. We are just wanted to find out the intensity of light which is coming out of P3. Okay, so by applying this, the intensity which is coming out of P2 will be by applying cos theta. So you are getting I2 is equal to I1 cos square theta 1. But what is I1? I1 is nothing but I0 by 2. So here I have written I0 by 2 into cos square theta 1 will be as it is. Now this is for the first polarizer and coming out of P2. Now the light will goes through P2 and come out of P3, right? So while passing through P3, component will be what? E30 is equal to E20 cos theta 2 will pass through, and the intensity will be I3 is equal to I0. Here it is as it is cos square theta 1, and new term will be cos square theta 2 by 2. So this is nothing but the intensity which is coming out of P3. What is that? That is nothing but I3 is equal to I0 cos square theta 1 cos square theta 2 by 2. Where that divided by 2 comes from, because when we say first polarized light is coming out of P1, it will be get half. So that is nothing but I1 will be I0 divided by 2. So that's why 2 is there. And where theta 1 and theta 2 comes from, as it is given in the numerical, that is angle for P2 is theta 1 and for P2 it is theta 2. So this is the equation which we got. Okay, so this is it for this numerical. So let's move towards the second one. Okay, here is the second one. The same theory we are going to apply, but it is in a very simple way. Okay, the unpolarized light with intensity I0 is incident on two Polaroids. The axis of first Polaroid is here, angle is given. This is very simple. So as intensity goes through first Polaroid, only two Polaroid are used, and the angle which is made to it is 50 degree with vertical and with horizontal, with second horizontal. So angle is fixed, which is 50. So we can put the value of angle in that equation of cos. Alright. So by applying all the theory which we have applied to numerical 1, so the first polarizer P1 will polarize the light and it will give you intensity, that is I0 by 2, right? This is we already have seen. Then by assuming the components of amplitude in electric field, so it will be E20 is equal to E10 cos theta 1. So I2 will be I1 cos square theta 1. So I0 cos square theta 1 by 2. So here instead of theta 1, I can write over here 50 degree. And I2, I1 will be as it is. Okay. So the resultant intensity which you are getting is I2 is equal to I0 by cos square of 50 degree by 2. So this is the answer. Actually first one is the theoretical part and second example is the numerical basis example of the same theory. So I hope you got it. So here is the third one, which is very easy. As you can see, it is one step forward. This can be asked for MCQ also by changing the refractive index. This is very easy. As we have seen Brewster's law. What is Brewster's law? It is nothing but polarizing angle is tan inverse of N2 by N1. That means ratio of refractive index of two mediums, right? So this is nothing but the example which deals with Brewster's law. So let's see what is that. For what angle of incidence will light incident on bucket filled with liquid having refractive index 1.5 be completely polarized after reflection? Now you have to get the numerical first, and then and only then you will come to know how exactly to solve it. Okay, so what they have given, for what angle of incidence, that means angle of incidence we are going to find out, by which a bucket which is filled of liquid having refractive index 1.5 will be completely polarized. Have you understood? A bucket is there which is full of liquid and the refractive index of that is nothing but 1.5. Second medium is air, so it is having refractive index obviously 1, and another one is 1.5 which is given. So when ray is incident on it, it will take reflection. Alright, so by what amount of angle the bucket which is full of liquid will completely get polarized? That is the angle, that means polarization angle that we have to consider. The reflected light will completely polarized when the angle of incidence is equal to Brewster's angle. This is the main conditions we have to consider. When all the light will be polarized when angle of incidence is equal to Brewster's angle. So Brewster's angle is theta b, which is nothing but tan inverse of n2 by n1. As n1 is 1 and n2 is 1.5, we have written over here. So we got this. So Brewster angle is tan inverse of 1.5. By using the logarithmic table, you can find out tan inverse of 1.5 in the table of natural tangents. and in natural tangents you are going to find out the number 1.5 over there, and at which column and which row you are getting 1.5, that is nothing but the angle in minutes of that tan. So this is nothing but we are getting from that, which is 56.31 degree. Okay, so this is very easy. In this you have to consider, or you have to remind one condition: when all the light will get polarized, only when the Brewster's angle is equal to angle of incidence, then and only then the whole light which is incidenting on the liquid will get polarized. Okay, so this is it. Next, here is the next one. Here, a plane wavefront of light of wavelength 5500 Armstrong unit is incident on two slits in a screen perpendicular to the direction of light rays. If the total separation between 10 bright fringes on screen 2 meter away is 2 centimeter, find the distance between the slits. First, you have to read the numerical again in your mind. What is that? Plane wavefront of light of wavelength 5500 Armstrong unit. So wavelength of light is used. Which kind of wavefront is being used? Plane. It is incidenting on a two slits in a screen perpendicular to the direction of light rays. Alright, two slits are there. The total separation of 10 bright fringes is given, which is 2 meter away from the screen. That means capital D, distance between slit and screen, which is 2 meter is given, and the total separation of 10 bright fringes is nothing but, what is that? Here it is. Total separation between 10 bright fringes is 2 centimeter. Okay, this is lambda, and this is capital D that is given. This is capital D. Okay, so given lambda is equal to 5500 Armstrong unit, D is equal to 2 meter, and distance between 10 fringes, as it is 10 fringes, so 2 centimeter is equal to what? 0.02. So as it is 10 fringes, you have to divide this 0.02 divided by 10. So you are getting this 0.002, as it is given as for 10 fringes. So by using the formula, this W is equal to lambda D by D, we have put, or by shuffling all the values, D will be what? D will come in this side, so it will be lambda D by W. Okay, what is lambda over here? 5500. As it is Armstrong unit, you have to convert it into meter, so that should be 10 raised to minus 10. This is raised to minus 10. I'm so sorry for this. 10 raised to minus 10 into, what is D? Capital D, it is 2 meter. Okay, divided by what? W. So what is W? 0.002. So by solving this all, you are getting value as 0.055 centimeter. Here is also single formula. By shuffling all the values, what we are going to calculate? Small d, and that small d is nothing but distance between two slits, and it is calculated as 0.055 centimeter. While doing any kind of numerical, just remember, first thing you have to write down given. For your convenience, there is no mark distribution for the given things. That is for your convenience. You have to write given, then as you write given, you will come to know either all the terms, all the given things are in single unit or not. If it is not, you have to convert all the numbers in a single unit. Like 5500 Armstrong unit, that should be converted into what? It should be converted into meters. if it is in millimeter, that you have to convert into meter. So that you will come to know when you write all the things in given. Okay, so after this, let's move towards the next numerical. Let's see on which term it is depends. Okay, now here we come along with Young's double slit experiment. I hope you remember Young's double slit experiment, in which a single beam of light is incident on a slit which is having two holes in it, and then light move forward in forward direction and gives you interference pattern on the given screen. Okay, so you are getting dark bright points over there, as it is an interference, and the distance between them is called as fringe width. Okay, so that is the Young's double slit experiment. Let's see what is given in this example. In double slit experiment, the difference in optical path lengths between the rays starting from two slits is given. Sorry, S1 and S2, and reaching point A on the screen is 0.0075 millimeter, and reaching to another point B on the screen on other side of central fringe is 0.0015 millimeter. I hope you got this. When light is going through two slits S1 and S2, they will move in their own way. Okay, suppose first point which is we are getting on the screen is A, and the second point which is to the another side of central band, which is point B. So they have given the path length or optical path length for reaching the light to point A and to reaching the point B. So we are going to calculate how many bright and dark fringes are observed between A and B. That we are going to observe. As we see the Young's double slit experiment, this is slit 1, slit 2, and here is the central band here. In this way we usually do the diagram of this, but what here it is given, S1 and S2 are starting to move forward the light wave, and suppose the point A is here, which we are getting, and point B is here because it is on two another sides. So we are going to find how many dark and bright fringes are there between A and B. That we are going to find out. In upper part it is darker and in lower part it is brighter. That we are going to consider. So let's see. Even the wavelength is given. So delta L, which is path difference, YD upon D is the general formula for this. For A, it is, I have written delta LA, which is YAD divided by D. Obviously small d will be same, capital D will be same, just what will change, y, small y, the distance from central to that single point, maybe dark, maybe bright. Okay, so first is given for A, it is 0.0075 millimeter, and that is for B is 0.00515 millimeter. So by shuffling this given formula, I got value for YA, which is 0.0075 D divided by small d, and even YB I got. Now we are going to find out the combined result, that is for dark and bright. So I have to add this both YA and YB. So by adding both YA and YB, I am getting this value 0.09 D by D millimeter. I haven't converted anything. Okay, So the width of bright and dark fringe, or the distance between two consecutive dark bands, or the distance between two consecutive bright or dark, is nothing but width. So this is given as W is equal to lambda d by d. By substituting values, we are getting this 15 answer. So between A and B, including the central one, 14 fringes are there between the bright fringes. 14 dark and 1 bright, because the central is obviously bright. So that will be counted as 1, and other 14 are dark. Why is it so? Because we are getting value as 15, which is odd integral multiple. That's why. Okay. So this is it for this Young's double slit experiment. So let's move towards the next one. This deals with resolving power. So it is for telescope. A telescope has an objective of diameter 2.5 meter. What is its angular resolution when it is observed at 5500 Armstrong unit? What things are given? Diameter is given. We are going to consider A as diameter. Wavelength is given, lambda. Both the things are given, and we are going to calculate what? The angular resolution. What is its angular resolution? So formula for angular resolution is delta theta, or a limit of resolution we can say for this. So this is delta theta is equal to 1.22 lambda divided by A. Very simple and very straightforward answer is that. But just you have to remember one thing, that when you calculate limit of resolution or angular resolution, that may be in terms of arcsec if it is asked. Otherwise you can write it in terms of radian itself. So how to convert this? I have just put at the values, that is 1.22, 1.22. Instead of lambda, it is 5.5 into 10 raised to minus 7. Instead of A, I have written 2.5. Simple calculation is there, and I am getting value as 2.684 into 10 to the power minus 7 radian. But if I am not wanting the answer in terms of radian, so what should I do? I have to convert it into arcsec. So what is the conversion for arcsec? The conversion from radian to arcsec is, you have to multiply this by 3600 into even 180. By multiplying this, you have to divide it by pi. By putting this, that will be converted into arcsec. By multiplying 3600 into 180 divided by pi. Value for pi is nothing but 3.14. So you are getting this value, 0.055 arcsec. Okay. Next one. What is the minimum distance between two objects which can be resolved by microscope having the visual angle of 30 degree when light of wavelength 500 nanometer is used? One step forward question, very easy. Minimum distance is given in theoretical part. The formula is given as d minimum is nothing but 0.61 lambda divided by tan beta. So as we have seen, there is only sine and cosine angles over there, but the angle is very smaller, we can write it in terms of tan. So the formula comes out to be d min is equal to 0.61 lambda divided by tan beta. So by substituting value, 0.61 will be as it is. Lambda is nothing but 500 nanometer. That has to be converted into meter. So that will be 500 into 10 raised to minus 9, or 5.0 into 10 raised to minus 7. Okay. Divided by tan of 30. By substituting value, I am getting this. Very easy. I hope you got this. Okay, so let's move towards the next one. I guess only two are remaining. Okay, eighth one. The monochromatic electromagnetic radiation from a distant source passes through a slit. The diffraction pattern is observed, obviously, on a screen which is 2.50 meter away from the slit. So capital D is given. If the width of the central maximum is 6 millimeter, W is given. What is the slit width if wavelength is 500 nanometer? 50 micrometer and 0.500 nanometer, that we are going to calculate. Different lambdas are given. Actually lambda value is same, just the difference in unit, so it will change accordingly. Alright, so let's see what is the general formula for that. General formula for the width from the central maximum is W is equal to 2 lambda D divided by A. But we are going to calculate small a, slit width. So by shuffling the formula, we are getting our required formula as A is equal to 2 lambda D by W. Now we are just going to change the value for lambda. Okay, so lambda for the first condition it is 500 Newton meter. By converted into meter, I am getting this, and by substituting all the values, which is 2 into 5 into 10 to the power minus 7 into 2.50 divided by 6 into 10 to the power minus 3. So here it is the answer, 0.416 millimeter. Same, in the same way I am just going to convert the mu m. To convert mu m, it should be multiplied by 10 raised to minus 6. So I am getting this. Okay, number will be same, just the differences in decimal point because the order will change. And the third one, I have not solved this because I want you to be solve this example, that is when lambda is 0.50 nanometer, what will be A? Value will be in ranging of 416, but what will be the final value, that you are going to tell me. Same, in the same way we are going to do, that is A is equal to 2 into 5 into what, 5 into 10 to the power minus 10, right, into 2.5 divided by 6 into 10 to the power minus 3. Then what will be the final answer? 4.16 into 10 to the power what? It will be minus 7. So answer for this is 4.16 into 10 to the power minus 7. Okay, so you can calculate this. You are going to calculate this. Ninth one. The optical path of ray of light of a given wavelength traveling distance 3 cm in flint glass having refractive index 1.6 is same that of traveling distance x centimeter through a medium having refractive index 1.25. Determine value of x. First of all, what is given? Two things are given which are same. What two things are given? The ray of light when incident on a flint glass which is having some refractive index and it is traveling a distance 3 centimeter, which is given. Okay, it will be same when it travels a distance of x centimeter and refractive index is another. So two conditions are given and we are going to find out x, and both the equations are same, that is given over here. So by using the basic formula for optical path, which is n into d medium. Okay, so two mediums are given, so n1d is equal to n2d we can write as it is given. n1 and n2 is given. D for the first one, it should be d1 and d2 actually. So here I will write d1 and d2. Okay, so n1 is 1.6 into d1 is 3, n2 is 1.25 and d2 is x that we are going to find out. So by shuffling this, we are getting x as 3.84 centimeter. Even this example is very easy. Okay, I hope you will got all this example. If I change the value over here as 4, as 1, as anything over here, you can find out this, because this is very easy. Okay, the last one. In Fraunhofer diffraction by a narrow slit, a screen is placed at a distance of 2 meter. Screen is placed at a distance, that means D is given from the lens to obtain the diffraction pattern. If the slit width is given, what is that? 0.2, which is W, and the first minimum is 5 mm, which is given. On the either side of central maximum, find the wavelength of light. As you will come to know what is given, it is very easy to find out what we are going to find out. That is W is equal to lambda D by A. As the condition is, what condition is given? Minimum, either side of central maximum. Okay, so that's why I'm going to use this formula, which is W is equal to lambda D upon A. So W is nothing but 0.2 into 10 raised to minus 3, as millimeter is over here. Then lambda will be as it is. Capital D is 2 meter. So I have written 2 divided by 5 millimeters. So 5 into 10 to the power minus 3 I have written. So by solving this, I am getting the value as lambda is equal to 5 into 10 raised to minus 7 meter, or you can write it as 5000 Armstrong unit. So this is the answer for this wavelength. Okay, so these are the numericals, and in a similar way you will solve the numericals. Many of them are related to all of these numericals, so just the value will be will be different, and you will get the another numerical. Okay, so I hope you all got all the numericals which we have solved in this part, and hereby I am declaring wave optics has been finished with theoretical part as well as numerical part. And yes, you are going to solve the numericals which are left, which I have not taken. Some of them I have taken from the textbook, which are solved and even unsolved, but the numericals which are unsolved, that you are going to solve, and in case of any query, in case of any problem, you are going to comment me and I will try to solve your problem. Okay, thank you so much.